Hello and welcome to this tutorial. In this one we're going to be looking at finding the speed in a series DC machine when conditions change. So you know that in a series DC machine you know that the torque speed relationship is an inverse relationship. It's like that. So what we're going to do is we're going to go through numerically and show how that can change over time depending on what the conditions are. So we'll take our series machine and we'll again draw it out over here. We've got our field resistance, our armature resistance, our idealized rotor. Now we know that it's got a voltage going into that and there's a current flowing there. And again, we can measure the voltage. That's really easy. We put a voltmeter across the terminals. We can measure the current. That's very easy. We put an ammeter in series with it, and we can measure the field resistance and the armature resistance by disconnecting the motor and measuring those. Again, it's fairly straightforward. We can also measure the rotational speed of the machine. That can be done quite easily. What we can't measure is the back EMF here that's generated, but we do have an expression that incorporates all of that, and we know that expression is the voltage here is the sum of that volt drop, that volt drop, and that volt drop. So that's the first way we've got of obtaining that. So that is the current times the field resistance plus the current times the armature resistance plus the back EMF. And we also have the standard expressions. The back EMF equals K phi times the rotor speed, which we can measure, and we can know that torque also equals K phi times the armature current. Now, for what we're going to be doing, these are pretty much all the equations we need. There is one thing to bear in mind though, and that is this is a series machine. The flux is being generated in the field, and so if the current changes, the flux will change. We can cut the long story short and say that flux is proportional to current, and that applies for significant parts of the machine's operation, but not always. If the machine is starting to saturate, for example, then obviously that's not the case. So I'm just going to put a qualified and just say usually, or often, or sometimes. In the purposes of this, it is. Now, if the conditions change, first of all, we'll go and put some numbers on this. So we'll say that the field resistance, we'll say that's been measured at being 0.15 of an ohm, and the armature resistance has been measured at being 0.05 of an ohm, and the input voltage, that's been measured, and we'll say that that's 250 volts, and we can measure the current in the existing situation. We'll call that 50 amps, and we'll say that the rotational speed of the machine, we'll call that 1200 RPM. So we can go through and we can see how the speed of this machine is going to change with a different current. As I said, current is proportional to flux. So if current goes up, if this doubles, this doubles. If this doubles, what happens to the speed? Now, if the current increases, we can see that we're going to get an increase here and here. So these two terms are going to change. The resistance is not going to change. The input voltage is not going to change. So if this goes up, then this has got to go down. The back EMF goes down and the current and the flux goes up. What happens to the speed? So that's what we're going to go through and we're going to find out. So the easiest way of approaching this is to go through and solve for the current situation, and then we'll change if you'll excuse the pun, we'll go through and solve for the existing situation, and then we'll go through and do some changes. So let's go. we know that using this one here, we can find the existing back EMF. So the back EMF at our 50 amp condition is the input voltage minus the current as it stands and the armature resistance minus the current as it stands and the field resistance, which is 200 volts minus 50 amps times 0.05 minus 50 times 0.15, and that is 200 minus 2.5 minus 7.5, which gives us 190. Now that, when you're going through and doing these, this is one of the first areas that a lot of people make mistakes, is they get things confused. This is the back EMF when the machine is drawing 50 amps. If the machine is not drawing 50 amps, then this back EMF will change. So that's why I've annotated it this way. It's the back EMF at 50 amps. And if we wanted to, we could also say that it's at 1,200 RPM. Okay? So now we know the back EMF. What we can then do is, knowing the speed, we can find the current K phi. So K phi at 50 amps, okay, is the back EMF at 50 amps. Again, we've got to make sure we're using the right ones, over the rotational speed at 50 amps. And that is 190 over 1,200 RPM, and that 1,200 RPM is 125.6 radians per second. 125.6. So that gives us a new K phi of 1.51. That's our K phi at 50 amps. So that's what we know of the machine. We can also go through and we can, if we wanted to, we can find out what torque is as well. This will come in handy later on. We know that torque is K phi times the armature current, which is 151 times 50, which gives us close enough to 75 Newton meters. We'll just put that aside, but what we've done now is we've pretty much know everything about the machine for its current situation operating at 50 amps. Now, if we go through and we change it to 75 amps, we know that the flux is proportional to current. So if we increase the current 75 amps, that's 1.5 times. So it's pretty simple to know that the K phi at 75 amps will be our ratio of our currents to our old K phi. So our new K phi at 75 amps will be a ratio of the new to the old times the old, and that there comes down to 2.265. So we now have two K phi numbers, the old one at 50 amps and the new one at 75. Now remember, at the beginning I said that our input voltage doesn't change, our resistances don't change, but if our current changes, our back EMF is going to change. So what we need to do now is go through and find our new back EMF, which we can find down here using our new K phi and our new rotor speed. Okay, so we go and find this. We find our new back EMF, and then from that, with our new K phi, we'll find our new rotor speed. So our new back EMF, EA at 75 amps, is going to be our input voltage still, minus our new current, which is 75, times our resistance, which hasn't changed, minus our new current, 75, times our resistance, which again still hasn't changed. And that comes down to 200 minus 3.75 minus 11.25, which gives us a total of 185 volts. And again, this machine is operating as a motor. Our back EMF, both of them, are less than our input voltage. That's good, and it's about 90%, that's fine. So, we now have our new speed, our new K-phi, sorry, our new back EMF, our new K-phi, we can find our new speed. So our new speed of the machine at 75 amps will be our back EMF at 75 over our K-phi at 75. And you've got to make sure you use the right values here. Okay. So our new back EMF is 185. Our new K-phi is 2.265. So that resolves down to 81.67 radians, which is the same as 780 RPM. So with a 1.5 increase in current, we've seen a significant drop in speed. That kind of makes sense because we do know that there is an inverse relationship here between speed and torque. So if we go through and find the new torque, remember this is the torque at 50, we've got our new K-phi, which is 2.265 over, sorry, times our current, which is 75, which gives us a new torque figure of 169.8 Newton meters. So we've got a significant drop in speed and a significant increase in current. This makes sense over here. What we could do is we could see if we can plot that somehow and see that there. So let's put torque and speed. Let's put torque on the bottom axis, shall we? And we'll put speed on this one here. So our torque numbers are going from 75 to 180. So if we make that, say, we go like that, we make each of those 50. So our first torque measurement is here at 75. And our second one here is 170. So 50, 100, 150, 170, it's about here somewhere. And our speed measurements, our two speeds were 780 and 2000. So if we make that, say 1,000, 1,200, it's between 700 and 1,200, sorry. So if we make that 500, we make that 1,000, and we make that 1,500, then we're going to have speed up here at 1,200, or just beneath that line, which is going to be here. And this one here, that's 500, we're at 780, about there. So we have this inverse relationship here. Here's one data point, and here's another data point. Now, my challenge to you is for you to go through and do this process that I've done and pick a different current. And again, continue to assume that current is proportional to flux. We're not getting outside that region. And get a third and a fourth one on there and put those on here and see where they go. And you will see that we reinforce this inverse relationship between speed and torque. That's my challenge to you. Okay? Thank you for watching. Look forward to seeing you again. Have a good day.